Welcome back to the weak base world. Let's do problem number 3. All right. A solution is prepared by adding 0.1 moles of sodium nitrate with enough water to make 2.50 liters. What is the pH of the solution? All right, it's phrased differently, but it's the exact same problem that we've been doing over and over. And step number 1 has not changed. I need an equilibrium equation. And so, seeing the word sodium right there, so I'm just going to get rid of that. Nitrite is that one. Oh, that's an anion. So anions react with water to make the weak acid and hydroxide. This is a Kb because it made hydroxide. All right, can I find the Kb? Now, in this case, I don't give you any equilibrium concentrations, and I should have said in the problem 25 degrees, but I'm going to go to my reference sheet and find Kb. And oh, guess what? I don't have a Kb, but I do have a Ka. And my Ka of nitrous acid is 4.5 times 10 to the minus fourth. And if you want to get the Kb, it's Kw divided by Ka. So my Kb is 2.2 times 10 to the minus 11th. Checking it again. 2.2 to the negative 11th. Okay. Now, what do we know? Let's see. A solution is prepared by adding 0.1 moles with enough water to make 0.25. I can't put moles in this ice table, and so up here I'm going to do a little 0.100 moles divided by 2.50 liters, and my concentration is, that's supposed to be a point. With 2 zeros, 0.0025. And, whoa, plug that in again. Well, that's an interesting. Oh, so didn't do that on purpose, but I am so used to seeing milliliters that I was trying to convert out of liters into milliliters to liters, and I should have just trusted my instincts the first time. That's just 2.5 liters. It's already in liters. So 0.1 divided by 2.5 is 0.04. Now, the reason I knew that is I was coming up with 40 as an initial concentration, and that just doesn't even make any sense. All right, so 0.0400. I didn't add anything to it. Minus x, x, x. And do I give you any equilibrium? Nope. So it's 0.400 minus x, x, and x. Okay, let's plug it in. 2.2 times 10 to the minus 11th is equal to x squared over 0.400 minus x. Gonna get rid of the x. All right, so 2.2 to the negative 11th times 0.4, square root it is 2.9, so 3.0 times 10 to the minus 6th. Do it again, 2.2, 11.4, square root 2.96 to the negative 6th. All right, let's check it. 0.400. Wow, definitely less than or equal to 5%. So that's okay. All right, now this is the first time the other one has really come into play. So do you see this negative 6? I'm getting right there on the brink of not being able to ignore water, but anything with a magnitude of a -6 or bigger, I'm going to ignore. So I'm right there at the edge. So yes, I'm still going to ignore it, but I am getting close. All right, so I now know X. Well, what is X? In this case, it's both concentrations, and zero point 0.4 minus that value is still just going to be 0.4 because it's not going to change it to significant figures. And I'm going to take the negative log of 3.0 times 10 to the minus 6. But guess what? This is not a pH, it's a pOH. And I get 5.53. And so 14 minus 5.53, the pH is 8.47. Did we expect a basic pH? Yes, we did. All right, now that's a fairly simple one. Literally, the only nifty part is instead of giving you a beginning concentration, I gave you moles and the final liters. I'm building up to when we're going to have to start doing dilutions. And that went so fast, I'm just going to do number 4 as well. All right, well, what will the pH of a 0.15 molar ammonia solution be? Balanced chemical equation. Kb. If you're getting bored at this point because you keep writing the same thing over and over, yes, you're exactly where you're supposed to be. When you get to the point where this is bored, you'll start to be able to go, oh, I don't need to fill out the whole table. I only need this much. But it's never wrong to do the whole thing. All right, this is a Kb. Can I find a Kb? Well, of course we can. Go to my list. And it is a fluke that the Kb of ammonia is the same as the Ka of vinegar. Just one of those fun flukes of nature. All right, I started out with 0.150. I didn't add anything to it. I didn't give you any equilibrium concentrations. So 1.8 times 10 to the minus fifth is equal to x squared over 0.150. I'm going to ignore the x. And my answer is 0.15 times 1.8 times 10 to the minus fifth. Square root it. It's 1.6 times 10 to the minus third. Double check. Yep, 1.6 times 10 to the minus third. All right, that was an assumption, so I'm going to check that I can use that assumption. (1.6%). Yay, it's less than or equal to 5%, so we're okay there. And it is greater than 10 to the minus sixth, so we're also okay on ignoring water. Okay, so what is x? In this case, it's 1.6 times 10 to the minus 3 and 1.6 times 10 to the minus 3. I know you're getting tired of me saying that, but in the future, that won't always be true. Okay, so you found x, but that doesn't necessarily mean that is the equilibrium concentration. So just beware. And then 0.15 minus that turns out to be 0.148. And what did I want to know? I wanted to know the pH, but I can't get that yet, but I can get the pOH. And the pOH is 2.80. And The pH is 14 minus 2.80. So the pH is 11.20. Were we expecting a basic pH? Why, yes. Yes, we were. Okay, and that's going to do it for our weak base problems. They are identical to our weak acid problems, but we tend to start getting close to that can we ignore water issue. All right, weak acids and bases. What fun. Until next time, jolly out.